This is the second week. We're going to be working with the exact same reaction we did last week in the same way with using the clock. So we're going to be determining this week the activation energy and the effect of a catalyst on an iodine clock reaction. So that's what we're going to be doing. So last week you figured out the rate equation for this, or the rate law for this particular set of reactions, and you found that it was rate equals that constant times the concentration of iodine, diiodide, times the concentration of persulfate, and they both had an exponent of 1. Well, this is the particular rate law we're going to be using today. Today, we're going to be working with the Arrhenius equation. And using the Arrhenius equation, we're going to be measuring K, and for reactions we run at a predetermined temperature. And once we have gathered that data, we're going to take the ln of K on the y-axis of a graph and 1 over T on the x-axis of the graph, right here. And that will give us our slope, which is m, equal to negative activation energy divided by R. And that, of course, is what we're looking for. We'll also be able to find the frequency factor, since the y-intercept, B, is ln of the frequency factor. So just like last week, this is the same first equation. That's the base equation that we're studying, and we're using a given concentration of thiosulfate that reacts with the iodine as it's created by the first reaction, and then gives that iodine back, the iodide back. So this is a cycle, and you used it last week. Persulfate iodide gives sulfate iodine, which is immediately gobbled up by the thiosulfate and continues to be until the thiosulfate is gone. The thiosulfate and the iodine have a molar ratio that we used, so we know exactly how many moles of iodine have been used when the thiosulfate is finally gone. How do we know when the thiosulfate is finally gone? Because at that point the iodine will react with the starch and form that dark blue, which we can time. So the same thing as last week. So like we said last week, rate equals K. I've written it differently here. Persulfate to the X, iodide to the Y. You found X and Y. They were 1. And now this week we're going to be finding K by using the rate and dividing it by the concentrations of our reactants. Then obviously we can find the ln of it and plot. Okay, so let's look a little closer at this. Here you can see we have 4 different temperatures, and they're roughly 10 degrees Celsius, 20 degrees Celsius, 30, and 40, and you will know exactly what they are. They will be to at least 1 decimal place. You're going to mix your solutions in a very similar way that you did last week, except for this week, your mixtures are already pre-made. Mixture A has the thiosulfate and the iodide. Mixture B has the persulfate and the sulfate. So nothing happens to these until you combine them together. But before you combine them together, it's a good thing to put in our indicator, which is starch. Okay, so you're simply going to be doing the same thing you did last week. using the burettes, adding your mixtures, and timing. From the moment you add the mixtures together, start your stopwatch. And when it turns dark blue, that's the end of your time. So again, I can't keep saying this. It's just like last week. Okay? There is one snag here, one thing that's very different from last week, and that is that we are having to keep these test tubes and this whole reaction at a certain temperature. You can't just take 2 room temperature samples and test tubes and put them and mix them together and put them in a 40-degree ice bath and say a 40-degree temperature bath and say, there, that was at 40, because those solutions needed time to warm up. So what you do is you get your test tubes with A and your test tubes with B, and you stick them in the temperature bath and warm them up for 5 minutes. At the end of that 5 minutes, you know what's in the starch in mixture A and what's in mixture B. Those 2 test tubes are going to be at this temperature. And that's important. We have to know the temperature they're at. So after they're temperature equilibrated, you can start the reaction doing the same thing you did last week, pouring the reactions back and forth, starting your timing immediately. Make sure you pour all of your mixture into a test tube, just like you did last week. Then the tube that has the mixture in it goes back into the constant temperature bath, and you have to watch for the first appearance of that blue again. Okay, and then you stop timing as soon as the blue color appears. Now, obviously, this, if we think about it, the amount of time that this reaction is going to take is going to differ depending on the temperature. We expect the coldest temperature bath to have the sample, or I should say coldest temperature sample, is going to have the longest reaction time, right? That's what we should expect. And if we expect the coldest temperature to have the longest reaction time, what do we expect of the warmest temperature sample? It's going to have the shortest reaction time. Okay, so the person next to you at the next bench who's doing the 40-degree water bath is going to have a shorter reaction time than you who are sitting at your bench with the 10-degree water bath. Okay, that's just the way it is, and it's fine. You'll be doing it the same way you did it last week with Mr. Proetta or your instructor. Okay, so 4 different temperatures. Constant temperature baths we've got. So the purpose of this experiment is to observe the effect of the temperature on the reaction rate. So careful temperature control we absolutely have to do. Now, okay, this goes on to give you some instructions, but I want to kind of get to these data sheets. What are we going to be doing here? I think we need some instructions. Well, let's look at the whole data sheet. Up here, you can see the concentrations for after mixing for persulfate and iodide, and I will help you walk through all of this in the Processing the Data video, but I want you to look at the data sheet. Now, this one said at the top, uncatalyzed. uncatalyzed. That means we're going to do one that without a catalyst. And what do we know about a catalyst? How does it affect a reaction? Remember, it lowers the activation energy. Exactly. So that's what we expect to see here. So for the low run temperatures, okay, took the temperature for each one, and I took the time for each one. The person at the next bench did room temperature, then mid temperature, high temperature. So you're all going to get to do a different temperature. Obviously, some of these are going to be more accurate than others. You may have to throw some out when you actually start averaging. Okay, so there's room, and those are just my data points that I got a few years ago. Once you get done working and collecting all that data, it's time to add the catalyst. Okay, you're going to find the same concentrations and the products of the concentrations and the I2 the same way you did last week. You're going to do the same 3 low runs, 3 room temperature runs, 3 middle temperature runs, and 3 high temperature runs. And then we get to start walking through the calculations. And this is what we're going to be doing next in the next video. So all I have left to say for this time is we're using the exact same solution, but instead of changing the concentrations this time, we're changing the temperature, which when you use the Arrhenius equation, when you plot the ln of K versus 1 over temperature, you can find that activation energy and you can find the frequency factor. So that's where you're headed this week.